Derivative rules the power rule. And as you will learn, this is really one of the king shortcuts in all of mathematics. It really is an amazing shortcut once we learn it. And the question is, how do we take the derivative of x to a power n? Well, let's go back to the definition. We know this is going to be the limit as h goes to 0 of f of x plus h minus f of x over h, and of course it's going to be the limit as h goes to 0 of x plus h to the n minus x to the n over h. And so this part of it, this first part where we're raising the binomial to the nth power, we're going to use the binomial theorem to expand that. And so what that's going to be is, limit as x goes to 0, h goes to 0, it's going to be x to the n plus n x to the n minus 1 times h plus, and I'm just going to say other stuff that has powers of h squared or higher. Okay, I don't have to worry about all of those, as we'll see. And of course, we're subtracting the lone x to the n. So the first term and the last term cancel. Now, every other term has an h in it, so we cancel all those h's. So we get the limit as h goes to 0 of n x to the n minus 1 plus, and all these other terms, this other stuff, all of it would still have at least one power of h, because if it had an h squared, even when one of the h's canceled, it would still have an h in it. And so all those terms that have an h in it are going to go to 0, and what we're going to be left with is nx to the n minus 1. And this is the amazing shortcut that the derivative of x to the n equals n times x to the n minus 1. And the thing that's super amazing about this is not only can we use this on an integer, say the derivative of x to the 5th is 5x to the 4th. It turns out we can also use this for negative exponents, we can use it for fractions, we can actually use it for all real numbers. It's actually quite amazing. So if we have the derivative, say, of x to the 1.7, well, the derivative of that would just be 1.7 times x to the 0.7. Okay, an absolute amazing shortcut. And one of the many consequences of this is that it enormously reduces the process of taking the derivative of polynomials. So for example, suppose we had a polynomial x to the 4th plus 15x squared, say. Well, we want to take the derivative of that. Well, that would just be the derivative of x to the 4th. Remember, we can split up the sum. With the constant multiple rule, we can take out the 15. So it's just going to be the derivative of x to the 4th plus 15 times the derivative of x squared. Well, that's going to be 4x cubed plus 15 times 2x, or in other words, 4x cubed plus 30x. And with the greatest of ease, we find that the derivative of x to the 4th plus 15x squared is 4x cubed plus 30x. So a truly amazing shortcut this is.